Hi everyone, my name is Ash, and I'd firstly like to thank the Zonta Foundation for believing in me, for supporting my research, and also giving me the opportunity to share what I do with everybody at the conference. My background is Indian. I lived in Australia for a while, and then I came to the US to study trajectory design and optimization under Professor Kathleen Howell at Purdue University. So the way I like to think about our line of work is that we're travel agents for the space industry. So how best can we transfer humans or even cargo between different planetary destinations? I'll talk a little bit about my research and then about where I'd like to take these efforts in the future. Okay, so as trajectory designers, we're often trying to balance very diverse and maybe even conflicting constraints. For example, do we expend a lot of propellant to get to our destination very quickly, or do we try to conserve propellant to be able to take more payloads such as scientific instruments or even cargo with us? So those are some of the balancing challenges we face in our industry today. There are many techniques to help us with these challenges. For example, if we're trying to go from this small Lyapunov orbit in black to this larger orbit that's in red, we could assume some kind of a thrust law, propagate the solutions, and see where that might take us. So as you can imagine, this trial and error process, which involves a lot of manual intervention, could take a lot of time, especially with one human involved in this loop. So in my research, what I've been looking into is, can we inform this design process with human intuition, but then incorporate computers and software agents to churn through all the infinitely many options to present us with some feasible solutions that we can then choose from and improve upon. This framework consists of 4 essential steps. The first one here is the propulsive capability of a spacecraft can help it reach a small region in space which is very large. And I call these regions the accessible regions because it's able to access any natural conditions that it finds in this volume at that instant in time. We then bring in pathfinding agents to sequence natural conditions from these areas to construct an end-to-end solution as you see here. So those first 3 steps give us some kind of an initial guess to begin with, but it still has discontinuities because all we've done so far is patch together these natural conditions. So then we look to more traditional techniques that can eliminate those discontinuities for us and give us an end-to-end solution for whichever spacecraft that we're interested in. What we're trying to do is go from departure to destination by sequencing these accessible regions, or ARs, along the way. So a natural question at this point is, what conditions should a spacecraft choose from within these regions when they become available? So that's when we bring in these pathfinding agents using reinforcement learning, where we introduce them to an environment that they're completely unfamiliar with. And their task is to go through these different states, construct the regions, and get us to where we'd like to go. At the beginning, they don't know where they are or the consequences of their actions, so they do a lot of exploration, which means they try out different states at random. Over time, though, some of those agents will reach the destination, so we will reward them for their accomplishments. And this is set up as a cooperative network where those successful agents then lay down reinforcements along the pathways that got them to the destination so that the other agents in the group can exploit the knowledge that some of these pathways may be better than others. So our end goal is to find that best trajectory or pathway that meets the user's global objectives. Here, it's a balance of time and mass, but it could also be meeting some risk requirements or anything that the user wishes to implement. So here's an example to see the framework in action. There are many families in space that exhibit similar characteristics. Here we have the Lyapunov family in black and the DRO family in green. And the task here is for us to go from this small little Lyapunov orbit to the larger DRO one. And And try to do that using a low-thrust spacecraft with these specifications on the bottom left. As a designer, I want to have some influence over what this design space looks like, so I set my global cost functions and also many other parameters in the framework. So what you will see next is that the agents, using the knowledge of the spacecraft and what the user desires, they will create this transfer themselves and present us with options. So these agents spiral out from the Lyapunov, they fly by the moon, which then boosts them out into the DRO orbit or our destination. So what they're doing is they're catching tiny little chunks of both these families, so they're sliding through the surface to reach the destination. And over time, they realize that it's beneficial to fly by the moon because it has the ability to slingshot them out towards the destination. Next, we have a very busy slide, but I do want to show that this capability is extendable to the spatial realm as well. Here we're trying to go from this green orbit to the black one. The green one is special because I don't know if many of you may have heard the name Southern L2 Near Rectilinear Halo Orbit. It's a very stable orbit in the moon's vicinity that also has good visibility of the Earth. So we're trying to send humans there in the near future. Maybe we want to have an outpost there, that can serve as a waypoint when we want to go to Mars later on. What I do want to draw your attention to here is the acceleration levels of these different spacecraft. NASA is trying to do many of these transfers with a very low acceleration here on the left because that's all we have access to at the present time given the readiness of our technology. What I would like to show with this framework is its ability to help us visualize and also quantify what we can do with more powerful spacecraft. So if we had 7 to 14 times the acceleration, we can start shaving this transfer time down to days from months. And so I believe it's useful in helping us think about what kind of technology developments we may need in the future and what the associated results might be. So to conclude, here is my design framework where the first 3 steps help us obtain some initial guess, which we can then improve upon using traditional techniques. The advantage is that by bringing in lots of these agents to look through infinitely many solutions for us, we can save a lot of time. And because we're presented with a variety of solutions, it can start helping us improve intuition for the design space. And that's very important if we're unfamiliar with a system, for example, the Martian system. So that's my research in a nutshell on the top left. And I'm also a very passionate space enthusiast and space advocate. And so what I'd like to do in the future is grow into a dependable leader in the industry and also help shape its future. So as such, I've been trying to embrace so many different opportunities in grad school, like the international design competitions. I've also interned at NASA JPL, helping them with mission planning options for the upcoming Mars sample return concept and also Europa lander concepts. I've worked with NASA Marshall, helping them with tools to try to analyze different types of architectures, mission architectures for going to Mars and the Moon. And lastly, I do believe space is for everybody. So as president of a student organization on campus, I helped organize forums and networking events where people could come and learn what space is really all about and how they could contribute. If we're trying to colonize Mars for humanity, I do believe everyone needs to be involved in this conversation and understand why we're doing it and all the challenges involved as well. And finally, I love doing outreach activities because I do believe it's really important to get the younger generation involved from a young age because they're the ones who are going to be the future leaders and shaping where this industry will head. So with that, I'd like to thank the Zonta Foundation again for all the support. I really appreciate it. If you'd like to get in touch with me with regards to my research, if you have any suggestions, or if you'd just like to chat, here is my email address down the bottom. So thank you very much.